Alright, so we're gonna prove that square root of 2 is irrational. I am gonna give a lot of definitions, but they're crucial to really deeply understand the proof. And so we're gonna prove this by contradiction. So assume the contrary. That is, assume that square root of 2 is rational. So then we can say square root of 2 equals p over q, where p and q are integers and q does not equal to 0. Okay. Further, assume that this fraction has been reduced to lowest terms. This is crucial because if p over q has been reduced to lowest terms, then we know that at most only one of them is even. So further assume this right here. Okay, so then 2 equals p squared over q squared. And p squared equals to 2 over q squared. And we're gonna box this right here because we're gonna be using it later in the proof. So p squared equals 2 over q squared, and since q squared is an integer, then p squared is even. And we have a theorem that says if the square of an even integer is even, then the integer itself is even. So then that means that p should be even too. So p equals to 2r, where r is an integer. Okay. So we've come to this, right? That p is even. Let's box that because we're gonna be using it later. We're gonna see how it all comes together. So thus p squared equals to 2r squared, which equals to 4r squared. And we know that p squared equals to 2q squared, so let's bring that back down instead of the p squared. So 2q squared equals to 4r squared. Which means that q squared equals to 2r squared, right? And so because r squared is an integer, then q squared is even. And so remember our theorem that if the square of an even integer is even, then the integer itself is even. So therefore, q is even too. So therefore, q equals to 2r. And remember that we know that r is an integer. And so we know that p is even, and we know that q right here is even as well. And since p and q are even, each has a divisor of 2, which is a contradiction since p over q has been reduced to lowest terms. So therefore, square root of 2 is irrational.